Hello, everyone, and welcome to another wonderful lecture on alkane nomenclature. So, last time we looked at simple substituted alkane species. So, for these species, we can identify their names by first identifying the length of the main carbon chain and then filling in exactly what our substituents are. So, for example, when we're looking at this case, we have a 5-carbon chain, so that means we have a pentane. And then we have a chloro at the 2 position and a fluoro at the 3. So we have 2-chloro, 3-fluoropentane. We also get more advanced molecular species, such as this substituted butane, where we have a 4-carbon chain, so that will be our root name. And then we have 2 iodines, 3 bromines, and a nitro. And we list those by position, separated by hyphens, comma separating numbers, alphabetically. So we have 1,3,4 tribromo, 2-nitro, 1,1-diiodobutane. And again, those prefixes will help us identify exactly what substituents we have and exactly where they're located. However, we often run into a more complex system, which is branching alkanes, where this time it's a little bit harder to identify what our core carbon chain is and what carbons are part of the substituents. So in order to do this, we need to first figure out how to handle this branching structure. So in this case, we have a main alkane structure, but we also have what are known as alkyl groups. So these are essentially alkanes as substituents. Now, in order to identify the alkyl substituents, first we need to identify what our common carbon backbone is. And to do this, we need to identify the longest continuous carbon chain. And then any side chains will be referred to as alkyl substituents. So in this case, our longest backbone is a 8-carbon species. 1, 2, 3, 4, 5, 6, 7, 8. Any other one will be a little bit shorter. So in this case, we have a nice octane carbon backbone. In the second case, it can be a little harder to identify. So one of the useful things is you take every branching point and you see how long it is in any given direction. So in this case, we have 1, 2, and a lot. So this means that my main carbon chain is going to go 1, 2, 3, 4, 5. Then from here, clearly going up is going to be the longest, 6, 7, 8. So again, even though it might not look like it, but this is also an octane species. Now, once we identify what my main chain is and what my substituents are, I can identify each of those side chains according to their length as if they were alkyl substituents. So how we do this is we name them like they were alkanes, but we replace that ane with an il or yl suffix. So we can then add each of those various suffixes, or each of these various alkyl substituents to that alkane name as prefixes, just like they were halogens. And again, just as before, what we're going to do is refer to number the binding sites of each of these substituents. And again, aim to keep these numbers as low as possible. And again, use multiplying prefixes if I have multiple identical substituents. And then again, place each of them alphabetically before the main chain with any corresponding binding sites separated by, again, commas and hyphens. So if we go back to this first octane species, we have 2 1-carbon chains. So these are both methyl groups. Meth is in 1 carbon, and now we replace that ane with il. So these are our methyl substituents. We also have a 2-carbon chain ethyl substituent. Now, in order to take care of my numbering, if I went from the left, it would be 1, 2, 3. If I went from the right, it'd be 1, 2, 3, 4. So we're going to have a 3,4 dimethyl species. And then we have a corresponding 5-ethyl. We can combine this all into one single name. Ethyl goes before methyl alphabetically, so it's a 5-methyl, 3,4 dimethyl octane species. Now, One of the things to watch out is that sometimes my substituents themselves may be branched, as we see in this left case, where I have a big long carbon chain, and then I have a nice 3-carbon substituent. So when trying to name these substituents, what I want to do is treat them kind of like they were alkanes, find the longest number. So again, 1, 2. So I have a meaning that I end up having a ethyl species. And then I'm going to refer to each of its substituents based on where it's attached. So I have a methyl group at the 1 position. And then I'm going to place the branching alkyl substituents as prefixes to my greater species. And again, everything here is going to be using that YL alkyl ending. So in this case, my main chain is an ethyl species, but I also have a 1-methyl substituent. So this means I have a 1-methyl ethyl species. Again, that end meaning that this is my root chain, and then I've attached a 1-methyl group to it. You can also widen this, including multiple substituents with the usual prefixes. So in this case, I have a butyl, or I have a propyl species, 1, 2, 3. And I have 2 methyl groups attached at that 1 position. So it's a 1,1 dimethyl propyl substituent. All right, so this is how I can name each of those substituents. Now let's bring this out into the broader perspective of adding these to a main chain species that often may be a little bit noisier. So each of these branch substituents will be placed inside of parentheses when I'm naming them. And they're going to be preceded by a number and a hyphen telling me exactly where they attached. And again, we can incorporate these into larger molecular names along with the other relevant substituents, following the same general rules of listing all of our substituents alphabetically. And again, if I have more than one chain that has the same length, the chain with more substituents is designated as the main chain. So for example, let's look at our branching point here. So I have one branching point here. If I track it out, I can go 1, 2 or 1, 2. So either way, I have a 2-carbon substituent. However, bromo, again, comes before the methyl, and it's a little bit bigger. So in this case, what we're going to have is our main chain is a 1, 2, 3, 4, 5, 6. I have a hexane main chain. And then my substituents is that 1-methyl ethyl species at the 1, 2, 3 position. And then I have a 2,5 dibromo. So again, putting this all together, I have a 2,5 dibromo 3,1-methyl ethyl hexane. So again, notice these names can get a little bit long, but you can break them into bits, allowing you to take the name and drawing a structure and vice versa. Now let's take a look at this longer species. So again, looking at our branching point. So we have 2 clear methyl substituents here. Now from here, I've got 1, 2, 3, 4 versus 1, 2, 3, 1, 2, 3. So in this case, I definitely have this as part of my main chain, and I have a nitro and a fluoro group here versus 2 methyls. So I'm going to put that nitro and fluoro as my main chain. So 1, 2, 3, 4, 5, 6, 7, 8. So I have an octane species. Then I still have that 1,1 dimethyl propyl species. But again, to minimize numbers, that nitro is going to designate this as my 1 carbon. So 1, 2, 3, 4. It's a 4,1,1 dimethyl propyl substituent. And then again, I have a nitro at the 2 and a fluoro at the 3 position. Bring this all together alphabetically. So I have a 3-fluoro, 4,1,1 dimethyl propyl, 2-nitrooctane. So again, the big trick with these IUPAC names is not to get overwhelmed, but break them down into their core components. And we can continue this process as I include cyclic alkanes. So these are essentially where I have a continuous carbon ring that has no double or triple bonds. So for example, I can have a cyclopropane where it's 3 carbons, cyclobutane with 4, and so on and so forth with 5, 6, 7, and 8 carbon chains. Again, no double or triple bonds, meaning I'm dealing with an alkane species. We can name each of these species based on size, but notice each time I include that cyclo prefix. So cyclopropane, bute, pent, hex, and so forth. However, one of the things you have to watch out for is that cycloalkanes, in addition to being our core root name, can also themselves be a substituent, in which case we use that alkyl suffix. So cyclopropane becomes a cyclopropyl group. Cyclobutane becomes a cyclobutyl. Cyclopentane becomes a pentyl. And cyclohexane becomes a cyclohexyl substituent. Now, let's go ahead and look how this gets incorporated into wider naming schemes. So this is specifically an issue if I have a molecule that contains both a straight chain and a cyclic component. So how do I know which one is the root name and which one is the substituent? So that root name is going to be based on the longest carbon chain, just like before. The trick here is that carbon atoms on a ring can't be counted as part of a linear chain. So I can't just start here, work my way around down on the chain. I have to compare the size of that ring versus the size of the chain. And again, the root name will go to whichever is longest, that straight chain or that ring. So in this case, I have a, and so that smaller, conversely, that smaller carbon species can be considered as the substituent. So if we do this, I have a 1, 2, 3, 4, 5, 6, 7, 8 carbon species versus a 5-membered ring. So my root name will be octane. And I have a cyclopentyl or 5-membered substituent. Bring this together along with that methyl extra methyl substituent. I have a 1, 2 cyclopentyl 4-methyl octane species. On the other side, we have a 1, 2, 3, 4, 5, 6, 7 member chain versus an 8-membered ring. So again, that 8-membered ring now becomes the core name, and we have this 7-member chain. But again, just like before, what we really are going to have is a hexyl substituent with a 1 position. Now, in each of these cases, it's fairly easy to, so in the second case, we don't have to reference exactly where on that ring this, the alkyl group is attached because every single position is equivalent. However, we often need to use some special rules when dealing with numbering the substituents on these cyclid alkanes. So again, that by default, that substituent will be placed on the C1 carbon. And so if I'm dealing with only a single substituent, then this means that I don't need to actually include any name because, again, all positions will be equivalent. So, for example, I don't need to say that it's 1 bromocyclohexane because that 1 is implicit. However, if I have multiple substituents, I have to work my way around clockwise so that I minimize that numbering. And again, if I will so in this case, I have a cyclohexane ring. And if I have multiple substituents on a single species, that single carbon, that becomes my C1. So here, I have only a single bromine and chlorine on these carbons, but I've got 2 methyl groups on this one. So this is a 1,1 dimethyl. And now I could go 1, 2, 3 to get to the next substituent, or 1, 2, 3, 4 to get to the next substituent. So we're going to choose to put the bromo on the 3. That means the chloro is on the 4. And when I add all of these together, it becomes 3 bromo, 4 chloro, 1,1 dimethyl. Again, working alphabetically, cyclohexane. Now, the last major group we're going to be dealing with is called ethers. So ethers are going to be essentially where I have 2 carbon chains attached to each other using an oxygen bridge. Now, these carbon chains can be identical as in this first case where I have two methyl groups, or they can be non-identical, where in this case I have a methyl and an ethyl. So how we go ahead and name these ethers is we treat the longer chain as our alkane using our corresponding rules. So in this case, I have a methane, and the second case, my longer chain is a ethane. Now, I name that oxygen-containing species as what's called an alkoxy substituent, where again, alkoxy indicates that I have an oxygen bound to an alkane. And these alkoxy substituents are named as if they were alkyl groups, but I replace that "-il" with an oxy. So in this case, I would have a methyl group, but since it's bound through an oxygen, it becomes a methoxy. And the same for the second case. Now, when combining their names together, I go ahead and use that methoxy as a prefix. So the alkoxy substituent gets used as a prefix on top of the alkane name. So the first one is a methoxymethane as opposed to a methoxyethane. So again, first portion is the alkoxy group, followed by that alkane root. Now, one of the things to watch out for is I may have an ether that contains both a cyclic and a linear substituent. So in this case, the root name goes to the longer chain. So in this case, I have an ethyl group versus a cyclohexane. So the root name goes to the cyclohexane with an ethoxy substituent. Now, if the root contains only one unique attachment site, again, as I said before, we don't need a number to indicate where it is. So I don't need to say one ethoxy cyclohexane. However, if there's multiple substituent locations, as in the case of this propane background, I could be bound at the 1 or the 2 position. So in this case, I need to use the locator number. So that methoxy is bound at the 2 position. So it becomes a 2-methoxy propane. Now, one of the things you should watch out for is that you may often encounter older common, or also known as trivial names. They refer to both of these substituents as alkyl groups. So in this case, again, we could treat this ether as a cyclohexyl ethyl ether. So again, this would be the older name, a cyclohexyl ethyl ether. Or in the second case, we have a methyl group, and then we have a even older name of the isopropyl group. So again, this would be an ethyl isopropyl ether. So again, I want you to be familiar with this nomenclature, not because I intend to use it, but because you will likely encounter it in the real world. So other common trivial names we may end up seeing a lot in either everyday life or other scientific fields that are useful to keep in mind. So some of the most common ones you may encounter besides those ether names are some of our more common alkyl substituents, and these might sound familiar. For example, if I have an isopropyl group, propyl means that I have a 3-carbon chain, iso means that I bound in the middle. Similarly, you can do the same thing with a butyl group. I have a 4-carbon chain, but I coordinated at the middle of essentially isopropyl group that has an extra substituent, rendering it from propyl to butyl. This is called a tert-butyl group. Similarly, you can imagine binding a butyl substituent in the middle, and this would be called a sec-butyl. So again, due to their convenience, these were the more common names, and you will often, because they are easier to write, see them in common vernacular. And again, one great example of this is good old isopropyl alcohol. I bound an alcohol to an isopropyl group. Again, I'll bring up other common names you may see in everyday life as we move forward, but that brings us to the end of our simple alkane substituents. So for the next inner chapter, I'll be talking about alkenes, alkynes, and arenes. Until then, take care.